Okay, we are now in the 14th lecture of the course and very close to the halfway mark. For me, that means very close to the end mark for that matter. So, today we will discuss graphical methods of dimensional synthesis. Okay, so last time we saw how we decide on the positions for which we tend to synthesize the mechanism. And now, in this lecture and the next, we will see the actual nitty-gritty of the method. Okay. So today, graphical, and next, in the next lecture, analytical. So forgot this one. So for the for the graphical method, we cannot go beyond three position synthesis. I mean, there are methods which go up to five position synthesis, but that would be too much for UG course. Even four position would be a little too much for UG course. Three position synthesis, graphical methods you can handle. And through this three position synthesis, I strive to give you the flavor of graphical methods. There are several methods known as graphical methods. There are several graphical methods. I am teaching you one of those, that is method of inversion. And for all the problems, we will use method of inversion, except for the dead center problem towards the end, which is special. Okay, so we start with motion generation, rigid body guidance. Okay, three position synthesis. More will become troublesome for graphical method. So we design a 4-bar mechanism to guide a rigid body, that is the coupler of the 4-bar mechanism, through three given positions, including orientations. So say the body in one configuration is like this, and in the second configuration it is like this, and in the third configuration it is like this. You know, if the connection points on this body were known, A1, B1, which in this position go to A2, B2, and in this position go to A3, B3, if these connection points are known and you are asked to find the connection points on the frame, then it is a fairly straightforward problem. Okay, so you say that if O2 is fixed and this body is moving such that A1 is sometimes here, sometimes here, sometimes here, then the three points must be on a circular arc with its center at O2, and that is very easy to find. You draw the perpendicular bisector of A1, A2 and perpendicular bisector of A2, A3, wherever they intersect, that gives you O2. Similarly, point B is going here, here, and here. Okay, so these three should be on an arc, on a circular arc, the center of which is O4. So you draw a perpendicular bisector of B1, B2, and the perpendicular bisector of B2, B3, wherever they cut, that will be O4. And if they don't cut, that means if they are parallel, then basically you get a prismatic pair. Okay, so this is quite straightforward. But mostly what happens is that the fixed pivot locations are given. Okay, and then you have to find out these two connections, and that is more troublesome. Okay. So fixed pivots O2 and O4 are selected for secure and available connection points. And then on the body to be guided, you look for suitable connection points. So O2 is given and you are looking for a suitable connection point A on the body. And similarly, another suitable connection point on the body, that point you call B, to connect to O4 with link 4. Okay. So this is troublesome. But then whatever we discussed here for this trivial problem, the same thing we will replicate there by inversion. In the inversion, we will keep the coupler fixed and try to move the mechanism along with the frame so as to get three positions for O2 and three positions for O4 for the same position, one of these three positions of A1, B1, I mean AB. So that is the method of inversion. So O2 and O4 are given and three positions of the coupler frame given. Now there is no AB. So for the coupler, we have a frame of reference, xi eta, in first configuration, second configuration, and third configuration. Now, this is too many dashed lines. Okay. So see the steps here, and on your paper, try to replicate those steps for a problem like this. So make note what is given. Point O2 is given, point O4 is given. Basically, the distance between the two is given. Okay, that settles the frame. And then for the body, you have three configurations. Then what you do, choose one of the positions where you will bring the other two positions. Okay, so you can choose 1, 2, 3, whichever one. So suppose we choose 1. So choose one of the positions of the coupler of the body to be guided, this frame. Okay, say 1. So say you choose 1. Now imagine that on this frame here there is a nice bed. Okay, 3 feet by 6 feet. Okay, so you are sitting there and looking at the world around. Then you feel tired, you sleep, and note that this entire frame along with your bed is mounted on a platform, which is the coupler of the 4-bar mechanism. After you have slept off on that 3 by 6 bed, the mechanism is slowly operated. Slowly, why? So that you don't get up. Slowly operated. Okay, and it is brought here. Now you are sleeping like this, 3 by 6. Okay, now you get up and look around. Earlier, you saw two flags here. You did not know that the flags have not moved because you were sleeping. So now your frame of reference is now here. So now you will be seeing those flags from this frame of reference. Okay, so you will feel that the two flags at O2 and O4 have been moved. So where they have gone? So now wherever you had seen them earlier, that you know. Okay, now wherever they would have gone, okay, array, O2 has gone a little on that side. Okay, that is what you would see. So where would that go? So you are thinking that you are still here. So what you will do from this frame of reference, thinking that you are here, you will feel that O2 has moved. So how? So for that, take a tracing sheet. Now this trace. Take a tracing sheet, put it on this, and trace this xi, eta, and wherever O2 you are now seeing, Okay, so I mean, sorry, wherever O2 was originally, that you trace, and O4 you trace. Okay, so this new frame and the O2 O4 which is given. Now you mark all those things on the tracing sheet. Now the view on the tracing sheet would look like this: the second configuration of the frame, and O2 here, O2 here. Now pick up that tracing sheet from here and put it in such a manner that the frame on the tracing sheet now coincides with this. Okay, and wherever O2 has now gone, you mark that point. Okay, what I have done, I have made a dash 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 like this. Okay, and another dash 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 like this, and then I have basically roughly taken the shape of this quadrilateral, this xi side, then this, and then this, and taken there that and placed it here. So like this, like this. So here O4 comes. Okay. So that is O4 to 1. That means position of O4 at the second position when inverted to the first position. And similarly, wherever this has gone, that is O2 to 1. That is position of point O2 in the second position when inverted to the first position. Okay. So what you do? You trace xi eta frame at the second position with O2 and O4, copy it to xi eta frame at the first position, and wherever O2 and O4 go, you take them this box. Okay. Similarly, now you sleep again, and the mechanism is again operated, and this fellow comes here, this frame, and now you again get up as usual, and then you see that O2 and O4 have been further moved. Some bloody fellow is moving those two flags. Okay, so you try to see where they have gone. So now you see this is the frame, and now O2 far away on this side corner, O4 that is also a little on that side only. Fine. So now go and put them. Now again trace this and those two oblique lines, and take the tracing sheet, put it here, and now those two oblique lines are here. Okay. So here comes O2 now, the flag. So O2 in the third position as inverted to the first position. Similarly, O4 in the third position as inverted to the first position. Now, from your bed frame of reference, you have seen O2 in three positions: originally, now, and before the two nice sweet naps. Okay. So the connection point on your bed frame with O2 must be at the point which is the center of the circular arc joining this, and this, right? So center of arc through original O2, which is O211, O221, and O231, that gives you A. Similarly, center of arc through original O4, which is O411, O421, O431, that is B. Now you get them. You see, this is a perpendicular bisector, and this is other perpendicular bisector, that gives you A, and O4 O4. This is one perpendicular bisector, and where is the other O4? This is one O4, and this is another O4. So that is the other perpendicular bisector, that gives you B. So you get O2, A, B, O4. Now the A and B that you have got, they are actually A1 and B1 because you brought everything here. Okay. So O2, A, B, O4 is the synthesized mechanism in position 1. Now this is motion generation, rigid body guidance. When you try to do path generation, coupler curve synthesis, then how does it work? You want a mechanism like this, in which in the coupler you get a point C, and then the prescription is again fixed points are easily, I mean fixed points are first selected so that you do not need connection point somewhere funny place. Okay, and you want your coupler point C to pass through these three given points. Okay, so O2 and O4 are given, C1, C2, C3 relative positions are given, and you want the connection points A and B. Unfortunately, with only 3 position synthesis, both A and B cannot be found. So you have to select one. So in path generation, and you will see in function generation also, in 3 position synthesis, too many things are actually selected. Okay, so which actually did not give me a lot of satisfaction. But anyway, so choose one of the two, A or B. Suppose B is chosen at the first position. So now come here. O2 is given, O4 is given, C1, C2, C3 are given, C1 here, C2 here, and C3 here. Fine. Now you have chosen B1. Fine. Now O4 is fixed and B1 you have chosen. O4B will be a link, right? So O4B1, O4B2, O4B3 must be constant because that's a rigid link. So with center at O4, you draw a huge circular arc on which B2, B3 also must lie. B1 is already lying. Okay, that is how you have drawn the circular arc. And where B2, B3 lies, that also you will know because ABC is another rigid link. So the distance BC in between cannot change. So when C1 was here, B1 was here. So you take this on your compass and from C2 cut this arc to get B2. From C3 cut this arc to get B3. So B1, B2, B3 are all located. See, now it is only A that you have to locate. Now that you have to locate A, so you see BC you have totally fixed because C was given, B you have fixed. Now A has to be changed, and that means it is the link 2 which has to dance. Okay, and you are going to fix this side. Okay, so invert position 2 to position 1. Trace B2C2O2. Here also we have chosen position 1 where we are synthesizing basically. So trace B2C2O2. Okay, B2C2O2. Okay, and take it to B1, C1, and wherever O2 goes. Okay, so wherever O2 goes, now see B2, C2, O2. This obtuse angle triangle, obtuse angle at C, I am making here. B1, C1, then obtuse angle wherever O2 goes. That is O2 to 1. position of O2 in the second position when inverted to the first position. Then again, on your tracing sheet, trace B3, C3, O2. Okay. Now this bigger obtuse angle we take and put B1, C1. Where is that? Oh, that I have not made here because it was. Oh yes, I have made B1, C1. This point. Okay. O2, 3, 1. So this arrow you see, I've written it here. So that obtuse angle I make here. And then you find three positions for O2, O2 original, which is basically O2, 1, 1. That is position of O2 in the first position inverted to the first position itself. That means not moved. And position of O2 in the second position when inverted to the first position. Position of O2 in the third inversion when inverted to the first position. And in the circular, at the center of the circular arc, passing through all three, A1 will lie. So you draw a perpendicular bisector, you draw another perpendicular bisector, and of course you know that the third perpendicular bisector also will go through the same point. So that gives you A1. And then you have got your mechanism. So O2, A1, B1, O4 is the mechanism in position 1. And A1, B1, C1 is the corresponding coupler. So O2, A1, B1, O4. This is the mechanism. And A1, B1, C1. So wherever C was given, with respect to that, A and B have come like this. Okay. So you have got path generation. Now you want function generation. Fine. Here also three positions. You need to have a mechanism for which the input output correlation is like this. And you see, starting point is arbitrary because which point of the body you are talking about making angle theta 2, that is up to you. So basically, you need to coordinate the differences. You need to coordinate theta 2, 1, 2, which is change from theta 2, 1 to theta 2, 2 with the corresponding change in theta 4 and the other change. So three position for function generation basically means two changes, and that is what you need to do. O2, O4 is given, and again here between A and B, one of them you have to choose. So you choose A1. Okay. So if you choose A1 and O2 is already given, so in the circular arc, A2 is located angle theta 2, 1, 2. A3 is also located from the first position angle theta 2, 1, 3. Okay. So O2 was given, O4 was given. You chose O2 A1 distance, and the first position was anyway arbitrary that you chose. Okay. So you got A1, and then A2, A3 you have got trivially. Now it is B, which you have to locate. That means basically you are trying to design the follower. Okay, link 4. And so in the inversion, that is what we will fix. Okay, so fix follower, B not known. Okay, so basically you will say that when you say fix follower, that means O4 is fixed. Okay, and that was originally given as fixed, it remains fixed, and one point on the link 4, which is actually supposed to be connected. Okay, that point when you locate, you will finish the design. So that body is fixed, and that body during operation, when not fixed, at these three positions have to have a line which rotates like this at position 1, this at position 2, this at position 3, with these angles between them, theta 412 and theta 413. Okay, so this is what we really need. Okay, this diagram is not important actually. There is nothing there. Okay, this is just visualization, our imagination. That is something of this sort we want finally. So draw inverted configurations of positions 2 and 3 back at position 1 of the follower. So for that, what you need to do, the rest of the mechanism O4, O2, A2, take it and turn it about O4. Wherever O2 goes, you don't care because you don't know anything with which distance O2 is fixed. Wherever A goes, that is the issue. So basically, when we say turn the rest of the mechanism O4, O2, A2, we basically mean turn O4, A2. The O2 also will be turning, but wherever it goes, it doesn't matter. So O4, A2, you turn by what? You see, you are taking it back here. No? So you have to go minus theta 412. So turn O4, O2, A2, basically O4, A2, about O4 by minus theta 412 to get A21. That is second position of A when converted to inverted to the first position. Similarly, O4, O2, A3, you turn about O4 because follower has to be fixed by this entire angle minus theta 413 to get A31. Now, as you have turned this, it has come here, and then you have turned A3 about O4 and it has gone there. Now you see A1 here, inverted position of A2 here, and inverted position of A3, A2, inverted position of A from the second position, yeah, A2. Inverted position of A2 here, inverted position of A3 here, all inverted at position 1. So the perpendicular bisectors cut at this point, and that gives you fixed distance AB. So this point is B, and the mechanism is O2 B1, sorry, O2 A1 B1 O4. Okay, so O2 A1 B1 O4 is the synthesized mechanism at position 1. Now function generation, rather than with 4-bar, you can do with slider crank also. Exactly the same steps will be followed, except for these two turnings, minus theta 412 and minus theta 413 about O4, you will use minus S12 and minus S13 along the sliding direction. About O4 gets replaced with along sliding direction, and these two get replaced with the corresponding sliding motion. Okay, and that leaves us with the only with the dead center problem. Okay, so you think over this diagram for 1 minute, and I will join you after that 1 minute. Here you freeze the video, and of course, whether you think over this slide for 1 minute or 4 minutes, it's up to you. So I pause the recording for a while. After coming back, okay. So in the dead center problem, all that you have to do is to coordinate this stroke of the slider. Okay, so I should have told you that I am showing you the dead center problem for slider crank, not for 4R. For a forward linkage, the dead center problem turns out to be uh, quite complicated. The book has it, and in some long time back, we used to cover it in the class also. But I mean, last 10-15 years, I have decided that we don't need that. Okay, I mean that's not all right for your uh, level. Okay, so you have to coordinate the stroke and quick return ratio for the crank motion. So what it means basically that the stroke is this. So why it is dead center problem? Because at one end of this slider motion there is a dead center, and at the other end there is another dead center. Basically links 2 and 3 get aligned at these two configurations, and that is why beyond that and beyond this it cannot go. Okay, so there are two ways in which links 2 and 3 can get aligned. One, if they are completely stretched, and two, if they are completely folded. So the angle between their lines is either 0 or pi. Okay, so that is the condition. So now it means that from one end to the other end, it takes some amount of time, and on the way back, it takes a different amount of time, less time. In the return path, it takes less time, and that is why it is called quick return mechanism. And now this less time, more time, that basically means that we are assuming that the crank, that is link 2, is driven at uniform speed. So more time and less time directly translate to crank motion, theta 2 motion. So this quick return ratio K, now this I have pointed out greater than 1, because which way to take the ratio, larger one by smaller one or the other way around, so that should be clear. Okay, so that is greater than 1. So K is theta 1 2 divided by 2 pi minus theta 1 2. So that basically means that theta 1 2 is more than pi. So suppose this is 200 degree, so then this will be 160 degree, and that means the quick return ratio is 200 by 160, that is 1.25. Okay, so if quick return ratio is given, then how to get the crank motion for the forward sliding and crank motion for the reverse sliding? So that you can get very easily. You take this 2 pi minus theta 1 to here, then that theta 1 to term you get here, club them together, you get k plus 1, divide with that k plus 1. So you get this 2 pi divided by k plus 1. So that way you determine theta 1 2. Fine. Now mechanism parameters L2, L3 and E. E is something which you select. Okay. And then the remaining two you determine. And how to determine them? After selecting E, you keep this angle theta 212 minus pi twice of that. Okay. So that you keep as phi. And then you start your construction. Locate P1, P2. Say P1, P2. at a distance S12. So this will be one end of the stroke, that will be the other end of the stroke. Slider, slider locations, you look, put, okay, at distance S12. O2 you don't know, where is O2? But you know one thing, O2 should be at a distance E from this stroke line, P1, P2, okay, line of the slider. So parallel to this, at a distance E, you make a horizontal line and keep it. Okay. Now this angle that you calculated here, you make a triangle on this side, isosceles triangle, okay, like this, okay, which makes this angle phi. Isosceles triangle, so you basically draw the perpendicular bisector of P1, P2, and then you want this angle phi here, right? So for that, actually you did not really need to do all these things, because you see, from this side itself, you could have done the job, because pi minus phi will be the sum of these two. And since isosceles, so these two will be same. So pi minus phi by 2. So basically, you do pi minus phi by 2. So with that, whatever angle comes, that angle you make here, here, and that's it. And if you do that, then you don't have to do perpendicular bisector either. Okay. But the point is that the angle phi is made here. That is something which we are trying to rub in. Okay. So that is why we say draw isosceles triangle P1, P2, PC with P1, C, P2 equal to phi, rather than telling what angle is here and here. Okay. Though that is straightforward to calculate and make. Okay. So we are rubbing in the point that angle phi is made here. Okay. Then the next step is the key step. With C as center and CP1 or CP2 as the radius, you draw a big circular arc. Okay, P1, P2, and continue. So wherever that cuts this locus of O2, call that point O2, because that is O2. Okay, because one locus of O2 you knew as this line parallel to P1, P2 at a distance E. Now another locus you have got this because of the logic of the construction. We will come to that. And then you see you have got one thing. What is this angle? Now you see P1, P2 is making angle phi at the center and making this angle at a point on the circumference. And the angle at the circumference made by this arc is half of this. That is why we have rubbed in that this is the so-called phi. So this little angle P1 O2 P2 is basically half of phi. That means theta 2 1 2 minus pi. And that is why we say that the completely extended position of the mechanism link 2 3 is this O2 to P1, and completely folded is this, because from here to here the angle will be how much? Pi plus this, and this angle is this. So pi plus this will be theta 2 1 2. That means in the completely extended position, it is O2 1 O2. The crank is in this direction, and in the completely folded position, it is here. So in between, the angle is theta 2, 1, 2. Okay, and that is pi plus 5 by 2. And this is what we have been targeting. Now that you have got O2, where is my cursor? Yeah, it's here. Now that you have got O2, join P1 O2 and extend it. And then with center O2 and radius O2 P2, draw another arc. And wherever that cuts the extension, call it D. And then midpoint of P1D is the position of A for this extreme. Okay. So basically, in the completely extended position, you have got L2 plus L3, and you know that this is L3 minus L2. So that same distance you make in this direction. So this is L3 minus L2, and this is L3 plus L2. So together it is twice L3. So you bisect it to get it here. So this is L3, and then therefore this is L2. Okay. So now you have got A1. So join P1 to O2 and extend with O2 as center and O2 P2 as radius. Draw circular arc to cut the extension at D. And midpoint of P1D is giving you A1, and O2 A1 P1 is one dead center. So O2 A2 P2 will be the other dead center. Okay, because then basically you will be joining P2 O2 and extending it till this point. Okay, till whatever length you have got from here. Basically, another circle is involved. That is a crank rotation circle. O2 A1 radius and this. Okay, so wherever that circle cuts with this extension, that gives you A2. Okay, so this is one dead center. That is another dead center. So here it is completely folded, and then as the crank turns, this has to go back. So that is the plan. So from P1 to P2, it comes through the crank rotation from here to all the way here. That is theta 2, 1, 2 greater than pi. And then in the return motion, it comes here like this, which is that much less than pi. Okay. So this is all for graphical methods of dimensional synthesis. In the next lecture, we will study analytical methods, which are much, much more powerful. They can do almost anything. Okay. So we'll see how.